Welcome to the lesson on winding a spherical pressure vessel, one of the most efficient geometric shapes for storing gases under high pressure. A sphere provides minimal shell weight for a given volume.
The single-pass winding pattern, one turn per turn, introduces a localized non-uniformity near the polar opening of a sphere. We call this local thickening, an uneven thickening that manifests itself simultaneously in both directions of the semi-geodetic coordinate system of the inner surface of rotation of the layer, U and V.
Could you describe what's happening in more detail?
Of course. Along the meridian, the thickness increases toward the pole, with a local peak at the turning point of the ribbon. Along the parallel, the material is distributed unevenly. It accumulates in the sector where winding begins, because each subsequent turn is adjacent to the previous one. With any other lead number, the first turns within the lead number divide the circumference into an integral number of sectors, and then subsequent turns are distributed evenly along this division. We get n small bulges instead of one large one.
So this is a fundamental limitation of single lead winding.
Yes, and this effect becomes more pronounced as the polar aperture decreases. A system solution requires increasing the lead number of the tapes.
How does WinderCAM solve this problem?
The solution lies in choosing a sufficiently large number of runs during the turn correction stage. Instead of one run per revolution, we use a fractional remainder of the turn period, which evenly distributes the material around the circumference. Each turn begins in its own sector, offset by an angle of 2*pi/n relative to the others, where n is the number of runs. The protrusions from different sets of turns are located in different sectors of the circumference. The material is evenly distributed along the polar coordinate, the twist angle.
Does using more loops completely eliminate the problem?
It significantly reduces it. With enough loops, the thickness approaches uniformity across the entire surface. The more loops used, the better the compensation. With 4 loops, the protrusion is divided into 4 sectors, with 8 into 8. The local maximum thickness approaches the average.
What about multi-zone winding?
This is an additional technique used alongside multi-zone winding. The sphere is divided into annular zones based on its geometry, and each zone is assigned its own winding angle. By arranging the polar thickenings one after the other, we reduce thickness variations along the meridian.
Why is thickness uniformity so important from a structural mechanics perspective?
First, you can apply a multi-pass pattern by directly specifying the number of passes. Second, it visualizes a more uniform material distribution as the number of passes increases. Third, you can divide the sphere into zones, each with its own angle determined by the pole hole radius. The program then generates a detailed layer thickness distribution along the meridian. Finally, it exports G-code for multi-loop and multi-zone winding, ready for your 3, 4, or 5-axis machine.
What are the practical applications of spherical vessels?
Spherical vessels are used in the aerospace industry, for example, gas accumulators for attitude control, in the power industry for storing compressed natural gas, in cryogenics for tanks with liquid helium or nitrogen, and in the chemical industry for high-pressure reactors.
In short, single-loop winding creates a problematic protrusion at the pole. Multi-loop winding distributes this protrusion across sectors, eliminating non-uniformity, and multi-zone winding reduces thickness variations by adjoining the thickenings of adjacent zones.
Exactly. With WinderCAM, you can explore both approaches, visualize the results, and export a proven CNC program for manufacturing, shaping multi-layer, multi-zone geometry into a technologically advanced and reliable design.
Thanks for watching. Stay tuned for the next example in our series.